Kia ora, and welcome to a lesson on Level 2 networks, specifically the shortest path, and more specifically using Dijkstra's algorithm to find the shortest path. There'll potentially be arguments as to the pronunciation of that name, but it's the way I've always been told to pronounce the name, so that's how I'm using it today. If you have an alternative method, which is more correct, good on you, but that's how I've been taught to say it. I apologise if it is incredibly wrong. Okay, so first of all, what is the shortest path? Well, the shortest path basically says if you want to go from one node to another node, what is the shortest way you can navigate this network to get from that node to the other node? Okay, so if I want to go from A to G, there's lots of different ways I can go from A to G. As shown in here, I can go very basic just around the outside. I can go crazy all over the place if I really wanted to. But obviously, we're trying to find the shortest version of that. So that's why we're going to use Dijkstra's algorithm. So looking at Dijkstra's algorithm, it says, give the starting node a value of 0. And this is an abridged version of Dijkstra's algorithm without an extra bit of work, but it's all we're going to need for our purposes. So we're going to use this, so give a starting node a value of 0. It then says to put a box around the node you are at, and then travel off the edges from the node and label the connected nodes with value of travel if there is no current value or the value that is there is higher than the new value. And that will sound very confusing for now, but I'll hopefully try and explain that a bit better whilst we're going through it. Step 4 says, looking at the network, select the next smallest valued node that is not boxed. If this is the end node, stop and inspect which root created this value. If not, repeat from step 2. So you keep bouncing back to step 2 until you're at the end, basically. So let's put this into practice, because those written instructions aren't necessarily going to be the easiest thing to start. So if I wanted to go from A to G, how will that look? So we're going to go to our start point. We're at A, and we're going to say at A we are 0, because we've not travelled anywhere. Okay. The next step says put a box around the node you're at, so I'm going to put a box around the 0. And then step 3 says travel off the edges from the node and label the connected nodes with value of travel if there's no current value or value there is the value there is higher than the new value. Okay, so from A I can go to B, which is 6. There is no number there, so I'm going to write the number 6. And from A I can also go to C, and there's no value there, so I'm going to write the number 7. Those are the only two places I can go from A. Okay, so I've done step 3 now, and I've labelled them because there's no value. Step 4 says, looking at network, select the next smallest valued node that is not boxed, assuming you're not selecting the end node, which is going to be G, so I'm not going to worry about that clause until we get to G. So we've done all the ways from A. We're now looking at a diagram again. There's no information on these nodes. Okay, there's no value here, so we're only considering these two nodes and their values, and we're going to select the smallest of those two values, which is the 6, and we're going to go back to step 2, which says put a box around that number. So we're putting a box around B. Okay, and now we're going to inspect from B. So we're now at B. We're going to look at all the different places we could go from B. So there's no point going back to A, because we've already put box there, distance was 0. However, from B, we could go to C. So we say 6 plus 6, which is 12 total, is 12 smaller than the 7. If it's not smaller than the 7, we're not going to do anything. If it was smaller than the 7, we would cross out the 7 and write our new number, but 12 is not smaller than 7, so we're not going to do that. So from B, we can also then travel to D, which is in total 8, because 6 plus 2 is 8. There's no number there, so I'm going to write the number 8 there. And then from B, we can also travel to E, which is 6 plus 5, which is 11. Again, there's no number there, so we're going to write the number there, 11. And now we have gone to every place we can go to from B. So there's no point looking at that one. This one wasn't smaller than 7, so we didn't do anything. This one had no number. This one had no number, so we wrote the total value so far travelled. Okay, now we've done all that. We're now going to look at our diagram again, and we're going to look at the places where we have numbers, 11, 8 and 7, and we're going to select the smallest of those three, which is down at C, 7, and we're going to put a box around it. Once we've put our box around it, we're going to say, from C, where can we go? So there's no point going to A because there's already a box. There's no point going to B because there's already a box. However, from C, we could go to D. So what is 7 plus 3? Well, 7 plus 3 is 10. Is it smaller than 8? No. So we're not going to write the 10 down, so we're going to leave that alone. But we can go from C to F. 7 plus 6 is 13. There's no number there, so we're going to write the number 13. Okay. Now we've considered all the paths from C. We're going to go back to looking at these numbers and choose our smallest. So the smallest here is this 8. Okay, so this number here is our smallest, be 8. Okay, so we're going to put a box around our 8. And now we're going to look at all the places we can go from D. So we can go from D to E, which is 4 more, which will take us to 12. It's not smaller than 11, so we're not going to choose it. From D to F, that's 8 plus 5, which is 13, which is the same as what's already there, so it doesn't matter which one of those two we're going to choose. Okay, but there's two ways of getting to that 13, and that's the only other place because the other paths are back to boxes. Okay, so now we've considered all the places we can go from D. We're going to go back to looking at the nodes where there's a value, 11 and 13, choosing the smaller of the two, which is the 11, and saying from here, where can we go? Well, we can either go down to F, which is 11 plus 3, which is 14. That's bigger, so we're not going to change this at all. And E to G is 7 more, so that is 18. Okay, that's going to stay there because it had no value. And now we've done all the places we can go from E. And by the way, this will probably, if you've just been watching this non-stop, you're probably sitting here going, oh, I kind of lost it about 2 minutes ago because he just kept talking. Pause the video, go back, maybe check the steps, but it's just following the same algorithm. I'm just constantly going to here, going back to 2, from 2 to 3 to 4 to back to 2. Okay. Now I'm at this point here where, again, I'm just selecting out these two. The smallest number is still 13, so I'm going to select my 13. Okay, and I'm going to say from F, there's only one place I can go because everywhere else is already boxed, which is to G. Is 13 plus 8 smaller than 18? No, because it's 21, so 21 is bigger. So that's our end. And now our final node, which is 18, which is actually where we're ending up, that is the value which will take us to there. Okay, so this is going to be 18, so we're going to put a box around it. Okay, unfortunately in this one I didn't get an opportunity to show you crossing out a value and replacing it with a new value. But if, when I inspected one of these edges, if it had been smaller, the total value, then I would have crossed out the value that was already there and written a new value to replace it. Okay, so the final step said, looking at the network, select the smallest valued node of the box. If this is the end node, stop and inspect which root created this value. So now we're going to do the inspect which root created this value. So from G, I'm going to work backwards. Okay, so I'm going to say which of these edges makes sense. So G is 18. If I was to go 8 back, that would take me to 10. However, this value here is not 10. So let's have a look at the other place I can go from G. Is 7 back this way. 18, 7 back is 11. So this is part of my path. Okay, because it makes sense. 18 minus 7 gave me 11. So this is true. From E, if I was to look going along these edges, which one of these three situations actually makes sense? Well, 11 minus 3 is not 13. 11 minus 4 is not 7. But 11 minus 5 is 6. So this path here, this 5 path, is part of my shortest path. And then from B, I go, is 6 minus 2 8? No, 6 minus 2 is 4. Is 6 minus 6 7? No, it is 0. And is 6 minus 6 0? Yes, it is. So this must also be part of my path. So my shortest path from A to G would go A to B to E to G and is equal to 18 kilometers, minutes, dollars, depending on whatever units you are using to describe your network. And I thought I couldn't add for a second, but no, I can add. 6 add 5 add 7 is 18, so that is true. So that is Dijkstra's algorithm to find the shortest path. Okay, you can find the shortest path via inspection. However, the maximum you can get for shortest path via inspection is achieved. So if I just looked at this network and gone, oh yeah, I can see A, B, E, G's, it's going to be the shortest at 18, I can say that and you'll get achieved. And there are other methods other than Dijkstra's algorithm. There's a tree diagram method. However, for merit and excellence, there's actually a bit more explanation that needs to go into it than Dijkstra's. And I find Dijkstra's overall the easiest of the methods to use for those higher awarded grades, as well as just for making sure you don't make a mistake. Okay, because the tree diagram method can be a bit fiddly and easy to make mistakes on. However, it does kind of make a bit more sense. Dijkstra's is very kind of abstracty. However, it does get you to the answer a bit easier. Okay, so this is Dijkstra's algorithm, the shortest path, and you can use it for any network to find the shortest path. Hopefully this kind of made sense. If not, maybe rewatch it, go a bit slower. And if you're wanting more videos on network, there's a video on traversability as well as a video on the minimum spanning tree for you to use. Hopefully this is helpful. Good luck and bye.